All right. A lot of today and tomorrow are going to be about establishing, we're going to be talking about some kind of complicated formulas. And so we're going to spend today and tomorrow talking about what the formulas mean and what specifically they tell us and what we're trying to measure with those formulas. And then we're going to kind of break the formula into pieces and what each of them represent and what each of them are before we start in the rest of the chapter doing the actual calculations themselves. So that's what we're going to look at between today and tomorrow. So, in the last chapter, most of the problems consisted of the following. I gave you a distribution and said that the population, that the distribution had this mean, this standard deviation. And then you talked about getting specific samples. You answered questions like, what's the probability of getting a random sample of 20 that has this mean in it, if this is what the population mean is? So I told you things about the population mean and then asked you questions about, if I get a sample that has a mean of this, how likely is that to happen? Or what's the mean and standard deviation of all samples of size 50? And then we had some formulas for that, and we worked through that. So that was the last chapter. We knew about the population. We used it to talk about what the samples might look like. This time, we're going to go the other direction. I'm going to tell you things about the sample, and you're going to use it to work backwards to tell me what the population might look like. And this is what we end up doing most of the time in the real world. Because in the real world, you usually don't know the whole data about the entire population. You take a sample to get an estimate of what you think the population is going to look like. And so, this slide is not in your notes. But it's starting to get at the idea. Is, let's say that I have this, I stored a mean on the calculator. And I drew a sample that has a specific mean, and I'm going to tell you what the standard deviation is, but I'm not going to tell you what the mean is. And so here's the sample that I got. And the sample had a mean of 240.79. Here's the idea. Is the actual mean guaranteed to be 240.79? No. It just happens that that was the sample I got. So, we can't say exactly what the mean is. But this can give us plausible values for what the mean is. Because if I got a sample that had a mean of 240, then, for example, the mean is probably not 5,000. It could be, but that's really unlikely. Probably not that high. It is probably somewhere in that kind of 240 range that we actually got for the mean. And so what we're going to do is we're going to use this 240.79 as the kind of center of my estimation of where I think the mean actually is. So we're going to use this sample to make a guess at what the actual population mean is. How would the sample mean vary if we took many simple random samples? Well, we talked about this in the last chapter. We're assuming that that mean is somewhere close to the mean of the population. And then standard deviation, we know this formula. It's standard deviation divided by square root of n. And so that's what the sample mean would look like. So we're using this sampling distribution to work backwards to try and figure out what range of values is reasonable for the population mean. And now we get to where you are at in your notes. So that value that we get in the sample is what's going to be called a point estimate. All right? It's a it's kind of a jargon fancy name for something that's really basic. You know, if we take a sample that we're trying to estimate what percent of people in Dixon High School are freshmen, and we get in our sample 23% of them, then our point estimate is going to be 23%. So it is just what is the estimate we are getting from our sample. That's what it's going to be. So when we build our confidence interval, which is what we're about to do, our interval is going to be centered around that sample mean or sample proportion or whatever we're getting from our sample. And we're going to call that value that it's centered around a point estimate. So going through a whole bunch of ideas here. If we have a 68, 95, 99.7 rule, if we got a standard deviation of 5, that means that 95% of the data should be within 2 standard deviations. And so if we go 10 to the left of our point estimate and 10 to the right of our point estimate, then we're going to get that actual population about 95% of the time. And so that's kind of the process or the idea that we are going through here. If we estimate that the mean lies somewhere 10 above or 10 below what we get in our sample, we'll be calculating an interval and using this method because of this 95% rule that is going to capture the true mean. It's going to be, the mean is going to be somewhere in between that interval about 95% of the time going through that method of sampling. If that did not make sense for now, don't worry. We're going to explain it about 5 different ways in 5 other slides here. Okay? So keep going, stick with me. One of them will catch on to you and make sense. The big idea. The sampling distribution tells us how close the sample mean is likely to be. We are going to use 3 pieces to build a confidence interval. Mark where I'm at here. Three different things. When we talk about the confidence interval, it's going to have 2 pieces to it. We are going to have an estimate, our point estimate, which is what we got from our sample, plus or minus some margin of error, which is going to depend on how far off we're okay with our estimate being and how wide our interval is going to be. And that's going to be determined by our third component, which is the confidence level. And that number is going to be a percentage And so last slide, it looked at if we, that was the idea behind a 95% confidence interval, which is actually what we're going to be making most of the time. Most of the time, we're going to be using 95%. And the idea, again, is that we are going to be looking for what this interval is going to give us is a range of values that we think the population mean actually falls in. And it's going to be centered at that point estimate. So going back to my percent of freshmen at Dixon High School, if we got 23% for our estimate, then we're going to be doing some calculations that we'll get to in a minute and getting a high and low end estimate centered around the 23% for where we think the actual population is, where we think the percentage of all the freshmen at Dixon High School actually is, based on our sample giving us 23%. That's the idea, is we're taking our sample and we're giving a range of values that we think these are a plausible range of values for where we think the population is at. If you're with me that far, then I'm feeling pretty good about where you're at today. But let's also talk about some of these more complicated ideas and start to build the foundations of them. Now, we choose 95% is like, why don't we want to choose 99 or 100%? Is because if you think about the normal distribution, if we wanted to capture 100% of the values, we'd have to go from negative infinity to positive infinity. Right? So usually we want to find a happy medium of values that are going to be correct estimates most of the time, balanced with we don't want too wide an interval as to be completely unhelpful. And giving us no information. If we say the percentage of freshmen in the high school falls somewhere between 5% and 65%, then that doesn't tell me very much. We want to keep it narrow enough that it's useful, but wide enough that it's going to be right most of the time. And usually that happy medium is somewhere in 90 to 95%. That's most of the confidence intervals that you'll see. All right. Here comes some interpretations. Here's another visualization of what we're talking about. Remember that different samples, because of sampling variability, different samples are going to get different results. And so, hypothetically, we could have some samples, we get a range of values centered around the estimate that we get from our sample, and because of how high or low an outlier it is, the estimate turns out to be wrong. And we didn't do anything wrong. It just happened that our sample turned out to be farther off than it would usually be. And so here's a visualization of that. Imagine each of these bars are different samples. And so let's say that this is the actual distribution. So this would be the actual sampling distribution. So here's where the population mean actually is. And here's a bunch of different samples I could take. And each of these bars is my confidence interval that I get from that sample. So it is my range of values that I think the center is at. Well, that range of values, this one, I have my interval in it. Got my interval. got my interval, got my interval. Uh-oh, it missed. We said the range of values was between here and here. Guess what? It's not. So sometimes just because of our different samples getting different results, you'll notice this high a value doesn't happen very often, but it could still happen. These different samples are giving me different point estimates and different intervals for where we think the value is. And what this means, what I mean by a certain percentage confidence intervals is going to be the percent of the time that the interval hits my population mean. That my interval will hit the target that it's supposed to. So if I say a 95% confidence interval, what I mean by what I'm going to end up saying is that I'm 95% confident that I've hit my target. That the mean is somewhere in this interval. And what I mean by 95% confident is that out of all the samples that I could take and construct an interval for them, 95% of those intervals are going to hit the target and have my mean in it. So we are talking about a percentage of the confidence intervals that will hit my target. So we are going to have two slightly different phrases that we are going to need to know how to interpret. And here's the general outline of what those interpretations will look like. More often, we're going to be interpreting this bottom one. Because you're going to get an answer for this interval, for this range of values that's between here and here. And our interpretation is going to be, we are this percent confident that our actual population mean is between, here's the two values. And so the important part of this bottom interpretation, is that it needs to include the percentage. So a phrase like, we are 95% confident, or we are 90% confident. That phrase needs to be included. You have to have the interval, so my lower and higher values of my estimate. And then you need to say that we're estimating the population parameter and give whatever that is in context. So for my freshman example, it might look something like, we are 95% confident that the actual percentage of students at Dixon High School who are freshmen falls between 20 and 26%. But you want to put this in terms of the population parameter. So that is the interpretation of the interval itself. The other thing you might get asked, and this is the trickier one, is to explain the confidence level. If you ever get asked, we can ask this two different ways. Number one is that it says to interpret the confidence level instead of the confidence interval. So pay really close attention to which one they're asking for. And the other way they ask for confidence level is to say, explain what 95% confident means in this context. So if you get asked to explain what the phrase this percent confident means, it's asking for confidence level. And the interpretation of the confidence level is this stuff I was talking about over here. It is the percent of all the samples I could take that will give me a confidence interval that hits the target. So I could take a hypothetical infinite amount of samples and get an infinite amount of confidence intervals. But because of the way the formula is going to work and the method that we're going to use, I know that out of all those confidence intervals, 95% of the intervals will hit the target. in multiple choice, there's going to be some distractor answers that you want to stay away from. Anything that talks about this as a probability, like saying that, you know, I have a 95% chance of being right or something like that, is wrong. It is the percent of all the confidence intervals I can make that will hit the target. Yes. Before that, I want you to take this problem here. In late 2009, the Pew Internet American Life Research asked a random sample of 2,253 U.S. adults, do you ever use Twitter or another service to share updates about yourself, see updates about others? In the sample, 19% said yes. This would be enough for us to construct the confidence interval and work out all the formulas. We're not going to do that here. We'll do that in the rest of Chapter 8. We'll do all the formulas and we'll get this exact interval. So we won't worry about that right now. I just want to work on, here's the answer. Can you interpret what it means? So give me the interpretation. This is I just gave you both of the templates. And so an outline of what the sentence should look like. So give me, in the context of this problem, what that sentence would be. And this is to give you a problem to practice with. Here's the confidence interval. Remember I said start with, we're 95% confident that. The sentence gets structured in a couple different ways. The thing you need to have in your, like I usually write them a little bit differently than the book writes them. Just the way I've always written them. The key parts. Number one, should have the phrase we are 95% confident or I'm 95% confident. You should be talking about the population parameter. You should not be talking about the sample. So it should talk about the parameter that we're measuring is the actual proportion of all U.S. adults that use Twitter. That's the parameter. So to recap, number one, we're looking for 95% confident. What's the actual parameter, the actual proportion of U.S. adults, is between, and then give your two boundaries, 0.167 and 0.213. The book is probably going to would write the same sentence as we're 95% confident that 0.167 and 0.213 captures the true proportion of U.S. adults that use Twitter. That says the same thing. It still has my three things. It's just in a different order. It's got 95% confident, and then it gives the range of values, and then it says these values estimate my parameter. Here's what it is. Just remember that all of these should be in the context of the problem. You don't just want to say the parameter or the mean or the proportion. You should say what the mean or the proportion are. What proportion are we measuring? The proportion of adults that use Twitter. Here comes the confidence level. So there's the other way to write it. Confidence level. 95% of all confidence intervals of the same sample size. So in other words, out of all the samples of 2,253, that was the sample size, of all the samples of that size that I could take, I could construct all of those possible confidence intervals. I just happened to pick this one. And what I'm saying is that 95% of all those confidence intervals is going to actually have the percentage of adults that use Twitter. So we're getting a range of values that we think is fairly reliable. That would actually have the population in it. Let me go ahead and jump down a little bit and give you the homework assignment. So that you have it.